So in our next recording, we are still going to talk about lipids. We're going to go into more detail now. So again, we have four classes of biomacromolecules: carbohydrates, lipids, proteins, and nucleic acids. And we've already talked about this idea of lipids being very hydrophobic. They're mostly hydrocarbons. Hydrocarbons form nonpolar covalent bonds in the molecule. So hydrogen and carbon, nonpolar covalent bond. Now we're going to address three different types of lipids: fats, phospholipids, and steroids. So fats are built from two types of smaller molecules. It's not a polymer, but we're still using this idea of having parts around that we can assemble and disassemble. And those two types are glycerol and fatty acids. So a glycerol is a 3-carbon alcohol, so the OH group is also called an alcohol group, that hydroxyl group attached to each carbon. And a fatty acid then is a long hydrocarbon with a carboxylic acid on the end. So again, go back, review your functional groups. So let's take a look at that. So what we see here again is our glycerol highlighted in gray, and then our fatty acid highlighted in yellow. And we can see with a dehydration synthesis reaction, though we're not building a polymer, we're using similar chemistry because it's more efficient to link the fatty acid to the glycerol. I look at this molecule down here at the bottom, this fat molecule, this triacylglycerol, and I just see a ton of energy. And you're going to see that later as we get into metabolism and talk about how we break this molecule down and turn it into the biological energy molecule ATP. And you're going to see that there is a tremendous amount of energy here. And again, that's why fats are so tasty. So fatty acids vary in their length, the hydrocarbon length. We'll talk about saturated versus unsaturated fatty acids. Those have impacts on your diet, but those topics I would encourage you again to take a nutrition course to understand them better. We're going to talk about them and introduce them now so that we can talk about them and use that knowledge later when we talk about their effects on the lipid bilayer of a cell membrane. But basically, if we look at a saturated fatty acid versus an unsaturated one, the saturated one is going to have all of the carbons linked with single bonds, meaning that every carbon has as many hydrogens as it can on it. While if I'm an unsaturated fat, I have a double bond between at least one set of carbons. Now what that does is put a kink into that otherwise relatively straight molecule. That's going to have an impact on how they affect the characteristics of a cell membrane. All right? So most animal fats tend to be saturated, and they tend to be solid at room temperature, while most plants have what we call oils, which is basically the same thing. They just happen to be liquid, and they happen to be unsaturated at room temperature. Ultimately, this kink in the chain that we see allows the molecules, or prevents the molecules from packing together tightly enough to become solid at a lower temperature. Right? So we'll keep that in mind. And again, this is a topic that you can learn a lot more about in a nutrition class. We will talk about then the hydrogenation process, and so this is a modification that the food industry has brought into to modify fats, and we can hydrogenate them. Unfortunately, to make them saturated, because it changes the texture and it tastes better to us to a certain extent. But what we oftentimes introduce then is the cis versus the trans fat bond, right? And this is then the orientation of that double bond. This is again something that you'll learn about more in organic chemistry. But if we look at the cis bond, cis means going to be on the same side, or they're near each other. These two hydrogens that we see here, they're on the same side of the bond, whereas trans means on opposite side or farther apart from each other. You can see that they're on opposite sides, those hydrogens there. And because of that, that has then physiological effects on how we break that fat down and how it functions in our body from a nutritional point of view, which again we don't have time to go into in this class. But that's kind of the source of that language, and that's the chemical structure of those molecules, so that now if you want to pursue that further, I encourage you to read more and learn deeply. Now again, fat's primary function is to store energy. 9 kilocalories per gram. It's more than twice as much as carbohydrates, and proteins happen to be the same. You can see this information on the back of any piece of food that you buy that has nutritional information. Right? So pick up a candy bar, see fat, carbohydrates, proteins, and you'll see each says fat has 9 kilocalories per gram. So we use this as a really good way to store energy because it's very condensed, and you can also use it as an insulator and a cushion for vital organs, right? So adipose tissue is then the type of tissue that we store fat in. Now you should go on and take an anatomy and physiology class and talk more about adipose tissue and the different kinds, right? So that's fats. Those are the high points of fats that I want you to know. Now the next lipid that we're going to study are called phospholipids. Now phospholipids are incredibly important because this is going to be the foundational molecule that makes up membranes. And membranes are going to make up cells. They're going to make up organelles. These are the delineation between compartments between the environment and living metabolism, in essence, on a cellular level. Now, phospholipids are great because they are amphipathic, right? And I'll show that word to you in just a couple slides here. But basically, they have a hydrophobic end, so we can see down here in yellow, again, highlighted our fatty acids. We know that's hydrocarbon. It's very hydrophobic. But then if we look at the gray area of this particular molecule that's highlighted, it has a hydrophilic head, water-loving, right? Why? Because we see charge. That phosphate group has charge. The choline has charge. And that charge wants to be with water. So now all of a sudden you've got a molecule that is both water-fearing and water-loving. And the special name for that is amphipathic. So it has some portion that's highly hydrophobic and some portion that's highly hydrophilic. And when you have that, all of a sudden you have very special properties when you try to put an amphipathic molecule into an aqueous environment. What's going to happen is that all the hydrophobic portions are going to want to get away from the water, and all the hydrophilic portions are going to want to be with water. So what you get is self-assembly, right? So again, what's driving this? Thermodynamics, right? The second law of thermodynamics. Entropy is driving the formation of what we see as a more ordered structure. But in essence, what we've done is reduce the order of the system to create this, what we call a lipid bilayer. Now, the hydrophobic tails are all kind of sequestered in the middle and hidden away from the water by the hydrophilic heads. So this then can form what we call micelles, and that's how soap works, liposomes, or what we think of as the phospholipid bilayer, which is going to be the foundational layer that makes up the cell membrane. True cell membrane is going to be much more complex than this, but this is where we're going to start, and we'll talk about that later as well. All right, so phospholipids, very important. Fats, storage of energy. Our last group we're going to say the least about. I want to introduce the idea of steroids to you. It's lipids in another form. They're characterized by rings, 4 fused rings of carbon, and these tend to be steroids. They can be hormones. The point that we're going to come up with these later is their role in affecting membrane fluidity. Right? So when we look at, again, this molecule, we're going to see our 4 characteristic rings. We have several different functional groups hanging off of them. That's going to affect how they work if they're working as a hormone. It's also going to affect how they play a role in the characteristics of any given membrane they're incorporated into. So for now, remember that steroids are the ring-like lipid, and we're going to see their biological role a little bit later in greater detail.